Hello everyone, my name is Rooji and I am a student at Indian Institute of Science. Today I am presenting a work on tracking an auto-regressive process of order 1 with limited communication. This is a joint work with Parimal Parag and Himanshu Tyagi. Here we deal with a problem of remote real-time tracking under communication constraints. First, let us look at the basic communication setup assumed in this work. We have an n-dimensional process xt sampled periodically. So this is illustrated in this first figure for a single dimension. Ideally, we need to communicate these samples across a channel and obtain a real-time estimate of the process at the decoder. We use the notation x hat t given t to denote the causal estimate of the process at time t given the communication received till time t. Now suppose this estimate look as shown in this second figure. So here we assume that the estimate is obtained by a simple sample and hold reconstruction of the obtained samples. But we impose certain communication constraints on the channel. We assume that the channel can transmit only NR bits per unit time. That is, each transmission of NR bits suffers a delay of 1 time unit each. As the channel is rate constrained, we cannot transmit these real valued samples without quantizing them. Hence, we have an encoder block in our block diagram. For faithful representation of these samples, we need to encode them using larger number of bits. But increasing the number of bits in turn increases the delay in transmission. So here we also illustrate how the same estimate might look with delay in transmission in the third figure. So we see that there is a trade-off between the precision with which we can encode each sample and the delay incurred in the reception of this information. We investigate this trade-off in this work. Let us elaborate a little bit about the source process. We consider an n-dimensional discrete source, that is, we have an auto-regressive process of order 1 as given here with process parameter alpha and the innovation process psi t. This innovation process psi t is IID, has 0 mean, and the covariance is such that the process xt has independent components with a fixed variance sigma square at all times. In addition, we assume that the process has bounded fourth moment. It is this process that we sample, encode, and send across a rate constrained channel. Now we describe the problem. So now we have some periodic samples from an auto-regressive process of order 1 and an encoder-decoder pair that we denote by phi and psi connected via a rate-limited channel. Due to the delay in channel, we see that at all times the decoder can access only the information sent till the previous time instant, and this communication till the previous time instant we denote by Ct minus 1. Also, as the channel is error-free, we can assume that the encoder always has access to the decoder state. In order to minimize the error in the real-time estimation, we must try to reduce the instantaneous tracking error given here. Equivalently, we may also try to maximize the tracking accuracy. Hence, we have formulated this optimum asymptotic maximum tracking accuracy as in here. Here, the tracking accuracy is 1 minus the time average of the instantaneous tracking error normalized with respect to the process variance. And the infimum is taken over all auto-regressive processes of order 1 with bounded fourth moments, and the soup is over all encoder-decoder pair. Our objective is to design an encoder-decoder pair that attains the optimum asymptotic maximum tracking accuracy. Observe that this optimal design will be universally optimal for all autoregressive processes of order 1 with bounded fourth moment. Let us now take a look at the prior works. We have a lot of works on related problems. We have some structural results on real-time encoders, and we have a lot of works on remote estimation under various types of communication constraints, and that on encoding stationary sources with rate-limited samples and on sequential coding for correlated sources. Only some of these works have been listed in here. The closest one to our work is the one by Kina and his group on sequential coding of Gauss-Markov sources. But these works do not consider the communication constraints and the resulting delay in the channel as in our work. Therefore, the trade-off between the precision in encoding and delay has not been studied in any of these works. So let's recall that the current setting is where we study the real-time estimation of the autoregressive process of order 1 when the information to the decoder is sent across a rate-limited channel with unit delay per channel use. Now let us discuss our achievability scheme. The basic encoding strategy that we adopt is similar to the differential predictive coding scheme found in literature. At the encoder, suppose XKS is the latest sample available. Then we take the difference between this latest sample and its current estimate at the decoder. And this estimation error, which we denote by Y, is what we encode and send across the channel. Now at the decoder, upon the reception of a new update, it is added to the current estimate of the latest sample in order to refine this estimate further. Now scaling this appropriately with the process parameter gives a real-time estimate of the process at the current time instant. So this actually tells us what is the update that we are sending across the channel. But this is not sufficient in our setting. Besides deciding what to send, we must also decide how often we should send these updates. We know that in any sampling interval, we have multiple transmission opportunities, and these figures show two external encoding strategies that can be adopted here. So in these two figures, we assume that the sampling period is 4. That is, we have a discrete source, and in every 4 time slots, we are taking in a sample. Now see the first picture. Here we try to send a new update in every transmission instance. Since we have only one channel used to send each update, the precision of each update is low, but then each of these updates will reach the decoder with a single time unit delay. This we call as a fast but loose scheme. On the other hand, in the second figure, we choose to send a single update in one entire sampling interval. Since we can use the channel several times, the precision of this update is higher, but it takes an entire sampling interval to reach the decoder. This we call as the slow and precise scheme. So here, the objective is to find out what is the optimal strategy to follow at the encoder. Is it to be fast but loose, or slow and precise, or an intermediate solution between the two? Incorporating these updation strategies, we propose the following encoding scheme that we call as the p-Successive update scheme. Here, the main idea is to fix an update period p and refine the estimate of the latest sample in every p time slots. For illustration, in this picture, we have used the sampling period to be 4 and the update period to be 2. Then, say at time 0, we start sending the difference between the 0th sample and its current estimate at the decoder. So we quantize this and we use the next 2 time slots to send this quantized estimation error. After 2 time slots, this is received at the decoder, and then we start sending the new update or the new estimation error for the zeroth sample. In the next sampling interval, we send updates about the estimation error of the next sample and so on. Note that if we set the update period to be equal to the sampling period itself, it gives us a slow but precise strategy. And if we set the update period to be 1, it is identical to the fast but loose strategy. Another very important aspect of the encoder is the quantizer that we use. In this work, we use a quantizer whose performance fits into the following structure. That is, expected quantization error when we try to quantize a vector y is bounded by the squared norm of this vector multiplied by a factor theta plus an additive error epsilon square. This we call as a theta epsilon quantizer. Let us look at an example. Here we see a scalar quantizer, a scalar uniform quantizer of resolution R working within the range minus n to m. Now if we are trying to quantize a scalar whose norm is bounded within this dynamic range of the quantizer, then we can see that this is a theta epsilon quantizer with this multiplication factor theta being 0 and the additive error epsilon square being m square 2 to the power minus 2r. Next, we see the particular realization of the theta epsilon quantizer that we use in our work. Our studies showed that in order to attain optimality, we need an ideal quantizer with the multiplication factor theta as 2 to the power minus 2r and the additive error epsilon square as 0. Now, if our estimation error was Gaussian, then using a Gaussian codebook would have solved this problem. But as this error vector is not Gaussian in our work, we adopt a randomized construction for the quantizer based on the spherical codes. This is actually a gain-shaped quantizer where the norm and the angle of the error vector is quantized separately and sent across the channel. Asymptotically, we show that this quantizer design achieves nearly our required performance guarantee. Our paper provides a more detailed account on this quantizer and its performance. So now let us check how the encoder works at each update instant. At each update instant, the encoder checks whether the estimation error is bounded or not. If it is bounded, then it proceeds to transmit the quantized estimation error. If not, then it transmits a special symbol indicating that the encoder has failed to send an update. So this happens because in case the vector is not bounded, then our theta epsilon quantizer will not be able to provide a faithful representation of this vector. And this transmission of this symbol facilitates our theoretical analysis. Next, at the decoder, it keeps on checking whether it has received the special symbol indicating the encoder failure or not. If it has not received this symbol, then it will proceed to update the real-time estimate by adding the new update to refine the estimate of the latest sample and then scaling it. But if it has received the special symbol, then it will declare the real-time estimate to be 0 for all subsequent time units. Next, we discuss the performance of our scheme. Analysis yields this bound for the instantaneous tracking error for our p-Successive update scheme. So here, this alpha and sigma square represents the process parameter and the process variance respectively, and this theta and epsilon comes from the theta epsilon quantizer that we use, and we have an additional factor beta here, which is the upper bound on the probability of encoder failure. See that this bound actually relates between the instantaneous tracking error at this particular time instant and the instantaneous tracking error for the last fetched sample. So here we see that this first term actually starts diminishing as time progresses since the procurement of the last sample. But on the other side, this second term, it is slowly building up as we are moving away in time from the sampling instant. Now, manipulation of this bound for a very large time horizon and finite dimension helps us to identify this function, which we term as the accuracy speed curve for a theta epsilon quantizer. When the probability of encoder failure is negligible, we see that maximizing this term reduces the average tracking error. Since this is a function of the update period, this gives us a guideline to choose the best value for the update period for any finite dimension. That is, choose the update period to be the one that maximizes the accuracy speed curve. For example, here we have plotted this accuracy speed curve for the ideal quantizer with the multiplication factor theta to be 2 to the power minus 2i and 0 additive error. And we see that the optimal value of the update period is the lowest value possible as this accuracy speed curve is decreasing in p. That is, here we must use the update period as 1, or in other words, we must use the fast but loose strategy here. Next, we present the results when the number of dimensions are asymptotically large. So this is our achievability result, and this is obtained by using the p-Successive update scheme for p equal to 1 along with the randomized codebook based gain shape quantizer that we discussed earlier. Here we see that the asymptotic maximum tracking accuracy is lower bounded by the product of these terms, and they depend only on the sampling period and the channel rate. We were also able to provide a matching converse bound as given here, and this was obtained for the Gauss-Markov processes, indicating that Gauss-Markov processes are the most difficult one to track. Since the bounds are matching, we see that the PSU scheme with P set as 1, that is the fast but loose strategy, is the optimal scheme universally for autoregressive processes of order 1. So to conclude, we have studied the real-time estimation of autoregressive processes of order 1 under communication constraints, and we provide an information theoretic upper bound for maximum tracking accuracy for a fixed rate and a fixed sampling frequency. And for a fixed rate and high dimensional setting, we see that the strategy of fast but loose is universally optimal. And we have also outlined the performance requirement of the quantizer needed to achieve this optimal performance. And when we have finite number of dimensions or in the non-asymptotic regime, then we see that the optimal strategy might differ from being fast but loose. And we also provide certain guidelines for choosing the suitable update frequency in such a setting. So with that, I would like to wind up my presentation, and thank you so much for listening.